Hey everyone. This lesson today is on standing waves, which you'll see is an example of resonance and superposition combined. So dealing with two of the topics we've talked about recently to combine together. So what you'll see here is a GIF runs really fast now on the new computers, but you have a wave going to the right and a wave going to the left. Okay, and so a standing wave will occur. This will be the result that we'll see in here. It's called a standing wave. Occurs when two identical waves are traveling in opposite directions in the same material. So in order to slow that down a little and analyze it, let's look at a freeze frame here of when the two waves are lined up completely out of phase. So I'm going to just put a line in or the rest position of the two springs or the two materials. And we can see that at this point here, there's a negative and a positive amplitude there. And so we'd have a negative amplitude combining and adding up with a positive amplitude. That's the superposition principle. So we're focusing on that aspect first, but that would combine to zero. If we went to another spot, we'd have maybe an amplitude of 0 and 0. Be another spot to see. So you'd have 0 plus 0 would also be 0. All the way along, these at that instant in time, everywhere. If we went to a spot here, we'd have an up and a down also, right? So we'd have a positive amplitude combining with a negative amplitude, also giving us 0. You can tell that everywhere along that spring would actually be 0 amplitude, but that's only for a brief instant in time. Okay, as the waves continue on in each of the directions, different overlapping results happen. So this one is when they're lined up in phase, the sort of two most interesting results. That one being kind of weird that there's like a freeze frame where looks like there's nothing going on in the spring. This one is the opposite of that. We're going to have an up with an up, and a down with a down, and so on in all these different spots, right? And then if you looked at, so let's do that. What do we have? A plus A equals 2A, so twice the amplitude, or combine and add up. We'd have a negative amplitude added to another negative amplitude. We get negative 2A, so twice the amplitude adding up in the downward direction. And then we could look at spots in between somewhere. Let's go with red. Let's look just sort of there. We have some down and some down adding up, right? So we'd have like maybe it's 0.6A and plus 0.6A, right? Going to give us 1.2A. So you do have these in-between areas as well. The result for that one, you can see you get the double up and the double down, if you will. And then we have the partial downs adding up to the total amount of down there, right? So each spot along the way you can just analyze very thoroughly with the superposition principle. Somewhere in between. If we look here, we have somewhere in between. Let's put the center on here. Here doesn't show up sometimes. Screenshot of that apparently. So let's just pick a spot. Let's go with peak right there, combining with that. Okay, so we're looking at an amplitude, like full amplitude, and it's adding to, half down maybe? So negative 0.5 amplitude. And so you can see you're going to end up with about half an amplitude up. And if you analyze all the different spots along the way, you'd end up with, a result like that, right? Where we're getting, instead of full amplitude, we're getting half amplitude going on, and so on in each of the spots along the way. And so, what's happening then is we have times when there's no wave, or times when there's lots of wave. We have times when there's sort of an in-between, and it's this result here that you see. Okay, so it's a little too fast for my liking, but we'll see other versions of this as well. But they're flopping back and forth between max up, max down. That maybe wasn't obvious from the previous slides that I was just showing you, but that's what we get. Okay, so the result here is that we have a wave pattern here. The key why we call it standing wave is we have this blue wave blue thing just seems to be flopping back and forth. You can't really see a left or right movement anymore. And so it doesn't really seem to have movement or a wave speed. And so it's looks like it's standing still. That's why it's called a standing wave. Right? This little applet might be a little easier to see here. So we got a red wave from the left, and a blue wave moving to the right. And so let's just focus on that version as well for now. If I put the net here, the net result, you can see that it adds up in the positive direction, adds up in the negative direction, adds up in the positive direction, adds up in the negative direction. And then there's a freeze frame here in the middle where the black line is right down the center. But that's the standing wave. That side to side movement motion gets sort of hidden by the way they overlap, because you're only seeing the overlap, of course, right? This is obviously here. Hopefully, you're recognizing from past stuff a transverse, so the vibrations are up and down in the material. Very obvious with the black one, anyways, and the waves are traveling. They are the same way in the red one as well. Let me show this red dot, for example. See how it's going up and down, right? So that the motion's up and down, but the wave is traveling to the left. Okay, so those are transverse waves, making a transverse standing wave. And then we'll see and hear actually a little bit more about this one here, but it's you can see how it's kind of bouncing back and forth as well, but it's a lot harder to visualize what's going on. That's actually a standing wave in a longitudinal type of wave. Okay, so that'll be something we'll look at later in the course. Okay, so obviously here longitudinal and transverse. As a nice review of things we've seen recently. So here we go. The demo with the spring. Let's go here. What I'm going to have in the video is I'm going to have my hand be the source of the wave. Then the second wave traveling the opposite direction is just going to naturally happen because of reflection. Okay, so here we go. Standing waves on the spring. I'll just narrate as I go here. So stretching the spring out, showing that if I send a little vibration, of course, the wave travels along. And so there's a very specific frequency that I have to move my hand at in order to get a standing wave pattern to show up nicely. If I just go at any random frequency, it's not necessarily going to make a nice pattern. So right there, it wasn't really the right frequency. And then my hand, I'm automatically fine-tuning the rate that I'm going at to sort of match the rate that the spring, quote unquote, wants to go at. It's the efficient transfer of energy of a vibration into a wave and so on, right? And so I switched to another frequency and again, didn't really jump right into a nice standing wave pattern right away. I had to sort of adjust the frequency, adjusting, and eventually I get the right frequency so that a nice standing wave pattern shows up. Okay, so we're going to be calling, let me see if I can get a nice freeze frame here. So that's not bad. So I'll take a picture of that one. We are going to be calling, don't need my mug in there, I guess. We're going to be calling these things. I'll just get to some of the labeling in that here as well, might as well. But you could picture there being a nice full wave pattern here of up and so on and back. Maybe that's a complete sine wave. It's in perspective, so it looks a little distorted. So the spring, if I wasn't bouncing it back and forth, it'd be like that. And so we have all the familiar stuff. You've got the amplitude out this way and the other way, of course. You've got this full wavelength going all the way from here all the way back, way up, I guess in this case, the wavelength, and so on. So those are familiar things. But what we have now is that after a little bit, of course, the wave pattern goes like this, right? This way. And so this now here, we're going to be calling this section here one loop. Okay, one loop of the vibration. And if you look, it's obviously half a wavelength. Okay. The other thing we're going to be naming is we have these spots here where the vibration particles, the particles in the spring vibrate back and forth at a maximum here. That's called an antinode. And the spots where they don't vibrate back and forth at all, it's called a node. Just specific page dedicated to that coming up, but I just wanted to give you some of the lingo as an intro here and see how it relates to the springs, just real life springs vibrating back and forth on the floor. All right, so here's that page. Your nodes are points where you have the constant destructive interference of the two waves, so there's no movement at all. So those spots that where the purple's pointing to, Then your antinodes are points where you have constant constructive interference, and it actually ends up alternating between constructive up and constructive down. Okay, those are your antinodes. And as I showed on the previous page as well, we have overall complete pattern. If I'm going through a vibration, I'm gonna go down and then up and then down, I guess is the order it would have been to send out that wave, right? So we have that complete pattern there. That's a complete cycle. Okay, so one complete cycle of that wave pattern or vibration. So that length, as they have labeled here, is the wavelength of it, right? That wavelength. If you can see it well on your screen or not, in my projector, it's pretty hard to see in the class, but I think you're able to see it on the monitor there. But that's a wavelength. If you notice, if we're going with lengths here, node to node, so node to node would be a half a wavelength. Just analyzing. This isn't something I want you to memorize. I just want you to be able to understand and label the spots. And then if someone said, "Oh, how far is it from an antinode to an antinode?" you just look and be like, "Well, it's half a wavelength. It's really, this thing's divided up into quarters, right?" I'll show you in a sec here. But that would be another half wavelength. And then if we went node to antinode, just right there to there, you can see a node to antinode, an antinode to a node to an antinode, and an antinode to a node in order there. Those are each 1/4 of a wavelength. There's 4 of them fits into the total. Okay. Yeah, that's for now. That's all I want there. When we're looking at measuring lengths, the nice thing about wavelength is you can literally just measure it. So you can just measure. You can just measure. Measure directly. Let's say. And so it's I don't know. It's 3 nodes. Distance between 3 nodes, I guess. That's not something, again, I'd want you to memorize. Just be able to look at the situation and say, well, I'm just going to measure a complete wavelength, right? The fact that it's a distance between 3 nodes is just reality that you know just by looking at the situation, not so much a tidbit fact that I want you to memorize. Other things you can get from this easily, of course, frequency, number over time. You just watch the vibration and measure them directly. If you look at the video, you could measure the number of cycles, how long it took for a certain number of cycles, and you could measure the frequency. Period would just be the opposite version of that, the reciprocal. Or you could just do the frequency number and do 1 divided by the frequency number. The other thing that's going to come up in the course that'll be important later on, I may as well mention it here, is that if you had this overall distance, say we had that was, I don't know, let's say it was 4 meters. That was 4 meters. Okay, so if that was 4 meters, then how do you figure out what the wavelength is? And the easiest would be to say, okay, well, we've got 1.5 wavelengths. This mathematically, you just set this up where it's like 1.5 wavelengths. So I guess 1.5 would be the easiest way to write that, because you have your full wavelength, then you have the extra half a wavelength. Because each loop, if you will, let's add that in as well, by the way. So these are loops of the vibration. That's a little less official, but they are half wavelengths. So we have 4 meters equals 1.5 wavelengths, right? And so in order to solve for what the wavelength would be, or to get that value, you just solve mathematically, divide by 1.5, and just takes the guesswork out of it. Set up an equation that you know is true, that the 4 meters equals 1.5 wavelengths, if that's what the measured length was, and you just do the division, right? So if I type in, put a hot link for the calculator here, but I used it earlier today, so it won't be how long here. If I did the 4 divided by the 1.5, right, gives me the answer of 2.66, or you could put that in terms of fractions, of course, but for now I'll just slap down the 2.667 or whatever. So 2.67 meters gives you the wavelength. So that comes up later in the course, being able to just do that logic. Easy enough, hopefully. But yeah, lots of definitions to kind of know to do with the thing and just be able to understand what you're looking at. So to give practice for that, I usually pull out the drill and the bungee that I set up for the class here, and sometimes I do it later on as a interesting intro demo to start the next lesson or whatever. But let's go for it here. So what you'll see is a bungee cord that's hooked to that doorknob, and then on the other end, it's hooked up onto a drill. You might see it later on in the video. Um, so at certain frequencies, I can get a nice standing wave going. So in fact, it's at the start, it had a pretty good pattern. I don't know if I just turned the drill off. I don't remember. It's from a little while ago, but you'll see at some point in the video, it's obvious that I basically changed the frequency slightly, and the amount of resonance, the amount of standing wave pattern energy reduces. So here I'm increasing the frequency to get to the point where 2 loops or a full wavelength. So the wavelength is literally from my device all the way to that doorknob. And you can see there a nice constant node in the middle, right there. Nice spot where there isn't movement. And then in the middle, in between those is an antinode. Okay, so if I keep going here, I'm going to go even faster frequency, sets up 3 loops. There's a node and so on. And then what I did there is I went a little faster yet. Okay, so let's see that again. I've got a nice 3-loop pattern going, and then I pull the trigger on the drill just a little more, go a little faster, and see how the pattern dissipates, like, goes away mostly. It's because resonance isn't happening at that point. It's like you're out of sync with the natural frequency. So if you're trying to push someone on a swing, let's say, and you push as they're coming back towards you, rather than waiting until they're ready to go, all that energy gets canceled out. You're pushing the opposite way that the object is ready to accelerate. So that is the drill, part of the drill demo stuff. Where's the rest here? So that end view there, this in the side view here, this student is asked basically if can I touch it, basically. And so went up and because it's sitting still, you can actually go up and touch that node, because it's a spot where it's not moving. And so more people wanted it on the action. So I've got multiple students up at the time, trying to touch those nodes. It's just kind of neat. Some people were enthused. Anyways, can't please everybody. And so here's the device. You can see here, this is it's like a circle on my drill, and it just jiggles back and forth. Not even very much. It's only going up and down like an inch or two, right? So if you watch it, it spins, and it's not vibrating a ton. The extra amplitude you get is because of resonance. So this is the source vibration. This is the material that has the vibration in it. The energy is building up. So the energy is transferring from the vibration into the material and building up when you're at specific frequencies. So it has all of the key points of resonance in it. And this is a slow motion video of it, so you can sort of see what's going on. Yeah. And so there was one point there where I showed it was 2 loops, I think, and then when I increased the frequency slightly, it kind of went almost to nothing, or maybe it was 3 went almost to nothing, and then it kicks up to 4 loops. Because if you're not at the right frequency, then resonance can't happen because you're not matching the natural frequency. Also things about the frequencies. So if I have the fundamental frequency making that 1 loop pattern, they call it a fundamental mode of vibration. And so that's your F0, or your base frequency. And so the British way of describing things is the base one is F0 or F0. Okay, the first one's the 0th term in a lot of parts of science, and it's more of a British influence. So then it turns out you double that frequency. So double that is making the 2 loop pattern, and then triple that frequency is making the 3 loop pattern. The numbers kind of make sense, right? Except that they name it, the base one is your fundamental, and then your first overtone has 2 loops, and your your second, my brain really wants to say 3 because of the 3 loops, right? Your second overtone has the 3 loops. So in North America, it's a little more common for us to start with the number 1 and count from there. And so your first harmonic, and then your second harmonic, and then your third harmonic have 1, 2, and 3 loops respectively. So that's kind of the way people tend to prefer here, because we're not used to the idea of the first one being the 0 starting point. But of course, all of our graphs start that way, so you can see why someone would do that. That's just a picture of the same stuff. This little demo, yeah, this one is kind of fun to play with as well. This one's very much like the drill and the bungee cord, so you can play around with it and make this thing oscillate and see what kind of pattern shows up. they've got some damping here, which means some friction. I'm going to move this to 0.84. I was playing around with it earlier. 0.84 seemed to be a pretty one of the frequencies that might match the natural frequency well. So if I don't have any friction there, you can see it's like really building up a lot of resonance. And then if I switch to 1 hertz, earlier anyways, at least it really started to fight. It would sort of start to cancel out and then build up a new pattern, but it's not doing it this time. I don't know why. As I go to new frequencies, there'll be times where it might a lot of the energy will dissipate because I'm fighting it. I think I actually have to have some damping actually to make it do what I want. Yeah, there we go. So basically, if I go back to 0.85 or so, you get a nice stable pattern. And even though this thing's moving up and down a certain amount, it maybe even more movement ends up in the system. And then when I bump it up to like 1, I'm putting more energy in the system at a higher, because I'm going higher frequency and so on. But see how the overall amplitude got smaller because it's sort of fighting. It's sort of in between different values. And if I jump around a bit, you can really see it like it kind of goes a bit, takes a little bit for the resonance to sort of build up. It's the idea what I'm trying to get across. So it was a pretty good one for a second there too, where the amplitude decreases a lot when you change the frequency because you end up pushing when you should be pulling and so on. You're just out of phase, right? So not matching the natural frequency. Application of this that you would know about, the xylophone, but the physics link to this is nice to sort of notice now. If you look at the way the geometry, certainly of this first one, picture the metal bar vibrating like that, and then like this. And the nice thing is then, in that scenario, you've got nodes there and there. And of course, why would you support the bar at the nodes? Because it's going to allow it to ring nice and long, right? Those are spots that aren't trying to bounce back and forth, and so you can touch them there. You can have the bar resting there, and so that's the kind of pattern we're looking at. And then if you look at the red one, it's obviously not it's not just 2 of this, right? So if you look at this pattern here, right, that pattern there and that pattern on each end, it'd be like maybe 3 or 4 of them fitting in there. And so picture maybe this pattern. Maybe it's this pattern or this one maybe for that red one, right? But still the same idea as we're supporting it at the nodes. So supports at nodes, because obviously then the bar isn't needing to move there, so you can touch it without grounding out a lot of the vibration and stopping it from ringing. In guitar strings, so in guitar strings, you have obviously the nut and the bridge, if you're familiar with the terminology, but the 2 ends of the string, and so it's going to vibrate back and forth with all sorts of different patterns. I have another applet coming up. I'll show. I might go to that one quick actually. Let me show that standing wave patterns. Second here. Standing wave patterns. Just 1 second here. I have a question from a student. All right, so here somewhere is, no, not there. Where did it go? This one. Here's the applet that shows all the different vibration patterns. And so let's look at the bottom row here where they're fixed on both ends. So a guitar string could vibrate up and then down, or it could vibrate up and down in 2 spots or in 3 spots and so on, just like I was looking at with the spring that I showed, right? So those different vibration patterns, you can picture, all of those being possible. And so there's something in guitar called a harmonic. When you're playing a guitar, if you want to do harmonics, what you would do is you would actually touch the center of the string. So you force it to be a node. And so picture this wanting to vibrate. Let's do that. And like this. So this is like one of the vibration patterns. And then it's like, or of course, like this. And so on, right? Lots of different patterns. But if you were to force this center spot to be a node, so if you touch here, just touch lightly to force it to be a node, right? What that's going to do is it's going to get rid of this. It's actually not going to get rid of. It's going to get rid of the main pattern. So that would get rid of this this fundamental pattern. And if you look at the other applet vibration patterns along the way, you know, it would get rid of any of them that have motion in the middle. So it's going to get rid of the third one. The fourth one would be okay. It would still be able to vibrate. It just reduces the number of vibrations that are possible, and that's going to be a key part of a discussion in a future lesson. Okay, so yeah, it would, if you touch it there, it's going to force like only this one. So that's just it would get rid of this pattern. Gets rid of many patterns. And then that's what changes the sound. It doesn't change the note, it changes the sound, the characteristics. So we will see more about that soon enough later in the course. So this little video here, some of it looks like it's fake, some of it looks like it could be real, but let's go bridge V here. Bridge, oh boy. Bridge, I searched it before, bridge V to get it to work. So this is Volgrad bridge, becomes a standing wave. And so you can see here, there's some kind of energy, possibly like an earthquake. Don't know what was causing it because there's no context at all, but you can picture there being spots there where you could say, okay, that's an antinode, and then there's a spot maybe be standing where it would be a node. Okay. So very strange. Traffic stopped, like, oh, not safe to go on the bridge right now because it's acting like a standing wave for some reason. So you're going a standing wave pattern. And we also saw this before too with the students on the bridge. So I'll go back to those videos because they are, we know the words now. Students on a bridge. Bridge. And so
well-timed forces create large oscillations.
So the well-timed forces part was about having the input vibration, the students jumping up and down, match the natural frequency of the way the bridge is able to vibrate.
Well-timed forces create large oscillations.
It creates large oscillations is the build-up of energy, right? The aspect of resonance that we're talking about. And then, what's the other one here? There we go. So 2 bridge resonance. Find my spot here.
Students are located at the antinodes to create the
So they're located
harmonic.
at the antinodes because they're literally jumping up and down with it. When I was doing the spring, I was actually at a node at the end, moving it back and down a little bit, but making lots of vibrations. Like, so my little vibration here is actually still counted as a node, but yeah, so they are at the antinodes, as he says.
Located at the antinodes to create the second harmonic. They input forces slowly in resonance with the bridge, and the amplitude slowly builds.
Used a lot of those same words, right? Yeah, so second harmonic, right? That's the one of the 2 loops like we talked about in class. And where's my file system here? Oh, and the other one's just the class 1 4th harmonic. That one. So there you go. There's a 4th harmonic. That looks a lot like that Volgrad bridge, doesn't it? Okay, so they managed to get a 4th harmonic going, which probably wasn't easy. Yeah, so kind of neat. And I already saw that one. That one I think is, you know, like if you set up a stand, well, I might talk about it later, but this one's a little weird. So if you want to click on that link and check it out, but basically I think it's a vertical standing wave in air, and basically you can get the droplets to kind of like surf on the wave, on the pressure waves or whatever, but not directly related. So I'm going to skip that one. You can check it out if you want. These are the questions that I would like you to do and ask questions about if needed, and post nice clear pictures of for me to see how are you doing. All right. Thanks very much for watching, and let me know if you need any help.